All right, here we go. This is lecture 14. I hope it's lecture 14 of CS161 summer 2021. Today we're going to talk a bit more about web attacks. So XSS, which is one of the big three web attacks you hear about. And then we're going to talk about UI attacks and manipulating the interface in ways that benefit the attacker. Before we get into that, we do have a couple of announcements. So we literally just released homework 5 as of like 10 minutes ago. So that will be due next Monday. It's a little bit shorter, so not that you should procrastinate on it, but hopefully it'll give you a bit of a break as you start working on project 2, which you hopefully already have. Sid's discussion tomorrow morning is canceled. So if you go to that one, feel free to attend one of the other ones that we have. I think either later this afternoon or tomorrow afternoon. We also have design reviews. So there is a calendar link that you can sign up at, and you'll get a 15-minute slot where you can just present the overall idea behind your design, and the TAs and or me and Perrin will have an opportunity to pick at it a bit and let you know if we see any immediate vulnerabilities. We've just released Project 1 write upgrades, so if you've been curious about that, there they are. And just as a reminder, the homework is due tonight. So homework 4 is due tonight, so please do it if you haven't already. The design doc draft for project 2 is due on Wednesday, and there's an optional lab that is out, which is due basically an eternity from now, basically the end of the semester, but we have to make it due at some point. So yeah, last time we talked about cookies. So cookies are a piece of data that are used to maintain state. So because HTTP is a stateless protocol, we need to construct something on top of it to give us this, shopping cart or logged in user. And these are set by the server and stored by the browser. They have a couple attributes that we talked about. And we have an overarching policy that says that only servers that use a domain that have the cookie as a domain suffix can access and set cookies. We used cookies to form sessions. So the first time we log in, the server gives us a cookie, and then in future requests, we give that cookie back to the server. The server looks it up and goes, oh, I remember this user, and gives you a logged in version of the web page. If the attacker manages to steal the session token, then they can log in as you. So we want to make sure we protect this as much as possible by making sure it's randomly and securely generated, and that your browser doesn't accidentally send cookies where it's not supposed to send them. I've just been DM'd really quickly by parents saying my internet's cutting out. I just realized I forgot to turn something off. So let me do that right now. I can see Perrin nodding, so that's a good sign. Yes, CRSRF. I need to make this full screen again. All right, here we go. So we also built an attack on top of this called CSRF or XSRF. This is basically just when an attacker exploits the session token that your browser has to perform an action as the victim. So the user logs in, the user receives the cookie, and then the attacker forces the victim's browser to make a request to the server. And because the browser is supposed to automatically attach cookies, it attaches the cookie, and then the attacker can force the user to do that authenticated action. The attacker can create these requests by either getting the victim to click on a link for something like a GET request, or for a POST request, the attacker can use JavaScript and have them navigate to the attacker site, which will have the browser automatically make the request. So there are a couple of different ways you can do this. This is definitely not an exhaustive list. In order to defend against this, we have something called a CSRF token. So this is another secret value, which is not the session token. And the user needs to attach the same value in order for the request to actually be valid. The attacker doesn't know this token because of this same origin policy, and this value isn't automatically attached by the browser. So there might be some piece of JavaScript that automatically attaches the CSRF token, or it might be a form value that is automatically submitted when it's sent back to the server. But the key is the attacker doesn't know this token and can't manually attach it like the origin of the web page can. You could also use the refer header, which is a very old typo. This would be just to check, make sure that the requests are coming from the same site as the site itself, but disallow requests that are coming from other sites. The issues with this is that this header is often removed for security or privacy reasons, so it's not a very reliable defense. And a newer defense that we've come up with is the same site cookie attribute. So this is just a flag that tells the browser only send this cookie if the request is coming from the same site as the domain of the origin, or the the request's origin is the same as the cookie's domain. This is newer and it's not implemented on all browsers, so it's also not a foolproof defense. Sorry, I'm trying over my words a little bit today. All right. So that was last time. Today we're going to talk about something called cross-site scripting, or XSS. This is, as it currently stands, the #1 security vulnerability that exists anywhere. So like I mentioned, you'll see this list a couple times during the course of the semester, and today we're touching on the top one in this list, which is cross-site scripting. So just as a review, we have the same origin policy. This says that two web pages with different origins can't access each other's resources. We don't want, say, the bank's web or the attacker's website to access the content in our bank's website, or vice versa. This is just another example. JavaScript on evil.com can't access the information on bank.com. So JavaScript gives us a very powerful language for running code in the web browser. This is run client-side, so it's executed by the browser itself, not by the server. And this code is only sent as a part of the response from the server. So this is used to manipulate web pages in different ways. It basically sits there to make it more interactive. So if you've ever played, maybe not a game per se, but interacted with more complex websites that do really fancy things, that's probably JavaScript that's working in the background to manipulate things. And these are sent using script tags. So almost all web pages nowadays are going to involve JavaScript, with the exception probably being a lot of professors' websites, which are sticking to age-old just HTML. But yeah, JavaScript is supported by all modern web browsers nowadays, so any vulnerabilities that target it are pretty widespread. And again, you don't need to remember JavaScript syntax. So what are some of the things that we can do with JavaScript? Remember that there's this alert function that makes something pop up. When the browser loads this, so it'll just load this string of text that includes the script tags in it. When it loads this, it will see, oh, there's a script tag in the response. I'm going to pause what I'm doing, run that script, and then in this case, when it runs it, it says, oh, happy birthday. So that is the processing of the JavaScript. So keep all of this in mind. The main thing that we'll want to keep in mind right now is that whenever the browser sees a script tag, it will run that. It doesn't care where it's coming from, because all it's receiving from the server is text, an HTML page. So I've just written a really quick HTTP handler in Go. You don't need to worry about any of the stuff that's grayed out. What we really care about here is this line, which just says, here's our really short HTML snippet. And in place of this %s, we just want to put in their name. So for example, let's say I want to go to vulnerable.com/hello and say name equals evanbot. So what we're going to do is we'll take this string, evanbot, and we'll drop it into this %s, just like we would with any format string in C. And the response I get back is what I want it to be. I get back the HTML opening tag, then the body, and it says hello evanbot. And if I render this, I actually get what I want. It says hello evanbot right here. And with this request, I've put in the name evanbot and got back what I want. So this all seems fine, but let's start playing around with how the browser is treating things. Because remember, the thing that the browser receives is just this string of text. There's no highlighting. It's just a sequence of characters. So what if we did something tricky? Let's say instead of just name equals evanbot, we'll actually say name equals, and then put this B tag here. So this is just a sequence of characters, which is the open bracket, the B, the close bracket, then evanbot, and then the same sequence to close it. And we see that, okay, this name is now this string. And this %s is just going to take this string and drop it in here. So when the server receives this response, it'll see HTML tag, body tag, hello, and then it'll see this B tag. Now, if you're not familiar with HTML, it's okay if you're not, but this is a tag that makes something bold. So when the browser receives this, it's going to say, now I need to make this bold because this is what I received in the response. So now I look at the web page and it says, hello, EvanBot, but EvanBot is now bolded. I've got a question. Does this occur with pre-processed pages like PHP as well? PHP, I'm actually not 100% sure. I've not coded in PHP, but if anyone else has in chat, feel free to let me know. We'll talk about how to defend against this in a moment in general, though. All right, so we know that if we put a B tag here, it will get bolded. Well, if we want to be a little bit more malicious, we could say, hello name equals script alert1 end script. And we know, again, this is just a string. So it gets put into this %s here, and the browser receives HTML body, hello, and then the script tag. Now, remember, this red highlighting doesn't actually exist. The browser sees the script tag and says, oh, this is a script tag. I am now going to treat whatever is inside as a script and execute that. So instead of getting a hello and then a name, what has happened is we've loaded the site and then it loaded the script tag, and now I have this alert box. This is an issue because it's fine if we have like alert1, but if this script is malicious and maybe it leaks your session token, or maybe it causes a malicious CSRF request, this is bad and we don't want it. So the core issue is that this input here is just text. So it's representing HTML control data. It's not just, sorry, I've contradicted this a little bit. It represents HTML, which is control data. And it's not just data as in I want to print these exact characters. So this is the core of the issue. Just as a note, this doesn't only happen with %s as well. Anytime you're manipulating HTML using string functions, you're vulnerable to this kind of attack. So here we're just saying, here's this half of the string plus name for concatenation plus the other half of the string. So we get the same output. So it's not just %s. I was just using it as an example, but you generally don't want to use string manipulation for control data like HTML. It was also, oh, this is from the earlier question. So does this happen with server-side processing? It depends. Most of the time, this is actually a server-side vulnerability. So yes, it definitely does happen on the server. As it definitely does happen because of the server's fault. That's what I have to say. All right, questions on how the basics of this attack work? The idea is pretty simple, and I probably would have written this code myself if I were just told to write this one day. So yeah. So the overall idea is that the attacker is able to add their own malicious JavaScript to a legitimate website through these techniques. That's why we call it cross-site scripting. Scripting means that the attacker can add their JavaScript. So because the legitimate website ends up sending the attacker's JavaScript to the browser, then the browser is attacking the malicious JavaScript that was written by the attacker. So because of this, the attacker has access to the information on the website itself. It subverts the same origin policy because, remember, the script runs with the origin of the site that loaded it, or in this case, the site that it's contained in because it's inline. And this subverts the same origin policy, which we don't want. There are two main types of XSS that we'll look at. One is called stored XSS, and one is called reflected XSS. So let's start with stored XSS. This is also called persistent XSS, and the main idea is that the attacker's JavaScript is somehow stored on a legitimate server, and then it's sent to the browser. So maybe it's put in a database entry somewhere as a comment or something else. So the example that we're using here is something like Facebook pages. anyone can load a Facebook page. And when you go to facebook.com, you see all of the content that is posted by all of your friends and whatnot. So that Facebook has to store content provided by the users, and the users could put in malicious, untrusted input. If the attacker puts JavaScript on their Facebook page, then anyone can load their feed and see that JavaScript in their browser. So if Facebook has an XSS vulnerability, then I, as an attacker, could put my JavaScript on my Facebook account, and then anyone who loads my page will load that script and then execute that script. And then maybe I can steal their Facebook cookie or something. This still requires the victim to load the page. So because the JavaScript is always executed by the client, it doesn't actually damage the server directly. Instead, it's an attack on the client and on the user who's using the client. So just to lay out all of the steps, we've got bank.com and then a victim and then an attacker. So for stored XSS, step 1 is to put some malicious script and have it stored in the server. So in this case, bank.com. Then later on, the victim goes and requests a page. I want to know what my bank balance is. And then the server says, all right, here is the page. And in this page is contained the malicious script that the attacker sent me earlier. The browser receives this and goes, there's a script tag in here. I'm going to execute that. And this script can do different things. Either it might steal valuable data and send it back to the attacker, because scripting languages can do that. Or maybe it'll make malicious requests on behalf of bank.com. So even if you have something like a CSRF token, remember the script is running with the origin of the bank.com domain. So we're able to make these malicious requests. Questions on stored XSS? All right. The other kind of XSS is reflected SSS. So in this case, the attacker causes the victim to send some input to a server, and then the server will reflect that input back into the response and send that back to the client. So the classic example here is something like a search box. If you go to google.com and say, oh, I'm looking for blueberries, then somewhere on the page it says, oh, maybe there were 10,000 results for blueberry. And you see, I had blueberry as an input and it gave me blueberry as an output. So maybe I could do something like, I want to search for script alert 1. And then I know the response will say 10,000 results for script alert 1. And if Google has an XSS vulnerability, then this will cause the script to run, and then in this case, it'll cause an alert window to pop up. Again, maybe it could be something more malicious. So in this case, we need the victim to make a request, and that request has to contain the injected JavaScript. So as a diagram, again, step 1, cause the victim to make a malicious request, maybe click on a link or something. This malicious request makes a request to a URL that the attacker has control over. This request with the input is then reflected back in the response. So now this response has that malicious script. The victim browser then goes and executes that malicious script, and then the same things can happen as before. Either you steal their data or you make malicious requests on their behalf. How would we get a request to be done on behalf of the user? Well, we can use some of these same techniques as CSRF in this case. Maybe we'll trick them into visiting the attacker's website, and then in that website is a iframe that makes that request. So that iframe is like, I want to load a page from bank.com/transfer money or something. You could make this iframe really small so that the victim doesn't notice it. And in this case, the code we'd have is like, say, iframe height equals 1, width equals 1. And the source is this malicious link here, which will cause that page to be loaded and then this script to be executed. We could also just have them click on a link. So if I send you a text with a link in it, more often than not, you're probably going to click on that link, even if you don't entirely know what that link is. If I trick you into visiting the attacker's website, that website could redirect to the XSS link. So I say, oh, click on, say, attacker.com/free money, and then that automatically redirects to this XSS link. And there are so many other ways that you could do this. I'm sure you guys could be creative and come up with like a list of 50 more, but these are just some of the examples. As a note, I know I was comparing it with CSRF earlier, but it's still different from CSRF. So the key is that XSS, in XSS, the response is sent from the server back to the client. The client parses that as HTML and causes malicious JavaScript to run on the client. Whereas for CSRF, we're forcing the client to make a request, and then that request is processed on the server, and then that causes a malicious action, say sending money or maybe logging in as the attacker. So it's a nuanced difference, but it's something that's important to keep in mind. And I know we've had confusion on this in the past. Questions on this? Right. Okay. How do we defend against this? I realize I forgot to animate this, so I've already kind of given you the answer. And I forgot to animate this in a way that makes it appear bullet by bullet. But the main idea is to use HTML sanitization. So remember that the core issue is that the browsers are parsing this untrusted data as control data. So maybe we can come up with certain sequences that represent the less than character or represent the greater than character rather than the control characters that they that would be used in actual HTML. So if we wanted to, in this case, all of these sequences will start with ampersand and end with a semicolon. So if we want to represent the less than character, which is often used in HTML, we're instead going to use ampersand LT semicolon. And when the browser sees this, it knows, okay, I just want a literal less than character. I don't want to open a new tag or anything. It's literally just this raw character. You can do the same thing with quote. So in this case, it's defined as ampersand QUOT semicolon. And there are many more escape sequences. There are certain lists of characters on the internet that you can find that are like, these are the ones you need to escape. And if you forget even just one of them, you'll end up with a big security vulnerability that can often be exploited, even if it's like something as simple as, say, a quotation mark or a backslash. As a side note, you should never do this escaping yourself. You should always rely on trusted libraries to do this for you, because if you write your own library, you're almost definitely going to forget some really subtle thing that leads to a security vulnerability. So you should never do this yourself. There is also something called the Content Security Policy, or CSP. The general idea is to give the browser additional instructions that say, only use resources from certain places. And like, here's a list of the places that you can use them from. So the standard approach would be to use something like disallow all inline scripts. So prevent those script tags from ever running. And that's an instruction I've given you at the very beginning. I would also say, only allow scripts from certain domains. So you're not allowed to run scripts from evil.com. You're only allowed to run scripts from maybe bank.com and I don't know, javascript.com that hosts some common JavaScript libraries. You can also use this for other content. It's not this part isn't super relevant for XSS, but you can also restrict iframes and images and so on and so forth if you really want to lock down what the attacker can do with an XSS vulnerability. This does rely on the browser. So if your browser is somehow coded poorly, it might not follow the CSP rules completely correctly, and then you'll still end up with a security vulnerability. So you can think of this more as a mitigation, like we talked about for buffer overflows, rather than a full-on defense. But it's still good to have in place because of defense in depth. All right, that actually brings us to the end of XSS. These are the two main defenses that we have, and the attack as a whole is actually relatively simple. But are there questions on how this works? All right. If we have additional time at the end, I might actually be able to throw together a XSS demo if you guys really want. I think there's also a website named Squiggler, which I don't know where it is right now, but it's basically a website that's intentionally coded poorly and it runs on your local computer and lets you play around with it, but I don't know where that is right now. So yeah, do we want to take a break now? I think it's a little bit early, so maybe we'll get through a couple more slides and then take a break a little later. All right, so that was a really deeply technical vulnerability. Now we're actually going to switch gears a little bit and talk about UI attacks. So instead of like exploiting vulnerabilities in the way that browsers parse websites, we're going to talk about the user a little bit. Now, this whole class is called user interface attacks or UI attacks. And the general theme is that you're tricking the user into thinking that they're doing one thing when they're actually doing another thing. And this all takes advantage of user interfaces, the UIs, which is the trusted path between the user and the computer. So the browser doesn't allow you to interact across origins. So it doesn't allow websites to interact across origins. So it won't allow bank.com to do things itself, but it trusts that, you know, this user knows what they're doing. So for example, I'll let them copy and paste data from bank.com and paste it into attacker.com. So the core theme is I don't trust the websites, but I trust the user. So if the websites can exploit the user, then we can start to exploit this trusted path and cause actions that maybe the user doesn't actually want to do, but they can't tell. So the security principle that you'll hopefully have in the back of your mind for all of this is consider human factors. And hopefully the reasons for that by now are fairly obvious. So there are two main types of UI attacks that we'll talk about. There's something called clickjacking, which is tricking the user to clicking on something that is from the attacker. And there's phishing, which is tricking the victim into sending the attacker their personal information. Just to clarify, there are definitely more classes of UI attacks, but these are just the ones that we're going to talk about. Okay, so clickjacking. Tricking the victim into clicking on something that's from the attacker. So maybe this is a download link, or maybe this is some button that, actually I can only think of download links right now. But the vulnerability is that the browser trusts that the user knows what they're clicking on. The browser trusts that anything that is clicked is obviously, you know, something the user intends to do. So this is the trusted path, and we can exploit this. Why would we want to steal clicks? So these are the reasons I was trying to think of earlier on the spot, but maybe it will download a malicious program, maybe for businesses or people who want likes, it could be a like on a Facebook page or a YouTube video. Maybe if you just want to cause damage to some online service, you could accidentally cause the user to delete their account. And so on and so forth. And there are similar reasons for why we'd want to steal keystrokes. So maybe we want to steal passwords from the user. Maybe we want to steal their credit card numbers. Basically anything that you would type into a web browser is something that the attacker might want to steal. So download buttons. If you have ever been on the internet and tried to download something, which I think is most of us, you might have come across sites that are like, oh, now I'm trying to download, in this case, Malwarebytes, and I get, okay, to download, I'm gonna, oh no, maybe it's, actually, these are all sort of download links. And where do I click in order to actually download? Because I know that hopefully one of these will actually give me the program I want, but what if one of these is actually, instead of anti-malware, it's just malware? And I download that and I run it and it causes issues. So here we're exploiting the fact that the user knows what they're clicking on, even though, you know, maybe they're unsure of what they're clicking on. Okay, for another kind of clickjacking, we can use something called iframes. So these are all sort of older screenshots. So if you go on berkeley.edu now, you probably won't see this, but just notice that if, in this example, we go to berkeley.edu and we hover over this page, we see that this goes to crowdfund.berkeley.edu. So maybe we want to be evil and we want to cause people to donate to Berkeley. I don't know. This analogy doesn't work very well. But let's load berkeley.edu in an iframe. So this would just be the HTML code for it. And we get this. So we're in our own site here. But if we hover over this iframe, we still get a link to crowdfund.berkeley.edu. So we can still get them to click on this iframe. And yeah, again, when we load the site, we can't cause a click ourselves because same origin policy. So we can't write code that automatically causes a click in here, but we can still cause the user to want to click in there. So maybe we put some really enticing contents. You know you want to click here because we're fairly uncreative when it comes to enticing content. This is underneath the iframe right now, so we can't see it. There's no way that this will entice people because Berkeley is asking nicely, but we're asking in a you want to click here sort of. I don't know where I'm going with the sentence, but maybe we can make this iframe transparent. So if we make it transparent, we can get them to see this enticing content. So now, if you look really closely, you can see you want to click here. And it's like, oh, it's so enticing, but obviously that's under something, and I don't want to click on this, Berkeley University of California thing. Like, what even is that? Well, we can make it even more transparent. So now it's like you almost can't tell that the Berkeley page is there. And if I click here, I'll go to crowdfund.berkeley.edu, even though I didn't mean to. But you can still see it. But I think by now most of you have realized we can take this all the way. If we make this iframe entirely transparent, now the site is just, you want to click here. Maybe this is a free money button or a download button for some fun game or something. I don't know. But when I click here, this click still registers for berkeley.edu. So we've caused the user to click on something they didn't mean to click on. For invisible iframes, we generally have 3 variants that we're working with. One might be to put the legitimate site over the visible enticing content. So this is what we were working with earlier. We can't see that we're clicking on berkeley.edu. We think we're clicking on some, enticing content. Variant 2, maybe we put the legitimate website under our own content. The victim thinks they're clicking on this legitimate site, but in actuality, they're clicking on our malicious website. So maybe I actually want to be on berkeley.edu. And I try to click on, if you look closely, there's an admissions button here. Maybe I really want to go to Berkeley. But I click on it, and it's actually the malicious website that says download the exe. So that's the second variant. And there's a third one that's, I think, really clever. You put the legitimate website under the malicious content, and the malicious content is partially obscuring the site. So we can change the appearance of this website, even though we have to deal with same origin policy. So we can't change the content of this website, but we can put content on top of the website and make it look like, we're only paying 15 cents for this, when in actuality, maybe we're paying $500 for something. And we agree to pay this, and we realize, oh no, we've just agreed to pay $500. So questions on, I guess, invisible iframes in general? All right, so that sort of exploits the dimensions of space, but we can get trickier. There's also a temporal attack that we can execute. So JavaScript has the ability to know the position of the cursor. And if, when we go to click on something, suddenly that content changes before we realize it, then our click ends up registering on something else. So the user ends up clicking on this malicious input, and they think they're just trying to download something interesting. So in this example, we just say, oh, please double click on this button to continue to your enticing content. So our cursor is here, and as we move over, suddenly, as we click, this frame pops up and says, clickjacking is requesting your permission to in this case, manage your contacts. So this popped up right as we were about to click it. And we clicked on it before we realized, oh, something popped up, and let me read what is happening here. So instead of manipulating space by overlaying or making things invisible, we're manipulating things in the time dimension. That's why this is called a temporal attack. There's another way to, so okay, that's the temporal attack. There's another way to do this, which is called cursor jacking. CSS has the ability to style the appearance of a cursor. So if you've gone on some websites and your cursor turns into like, I don't know, maybe a hand or a, I don't know, a heart. I don't know what people make cursors nowadays. But then that would be CSS that's changing the appearance of your cursor. And again, the JavaScript can track the position of your cursor. So if we tweak the appearance in just the right way, we can actually create a fake cursor and trick users into clicking on things. So, oops, I did it again. So give me one moment while sorry, I didn't have my door closed and I needed to do that really quickly before the dogs came in. So here we create a fake cursor. Maybe this is with JavaScript or CSS. And then our real cursor is still somewhere else. So maybe we've hidden it entirely with CSS, or at the very least made it less visible. And as we go to click on something, maybe, oh, we see this is our real cursor, so I want to click on this play now button. But in actuality, my cursor is like 2 feet to the right, and I'm actually about to click on this download exe button. So if you were to see this, what would you think you're clicking on? In most examples, this isn't going to be like a semi-transparent hand. It's actually just going to be completely black, or maybe they made it a 1x1 pixel to make it really hard to see. Not completely black, completely transparent. So we have lots of ways to mess with things. We have lots of ways to get the users to click on things that they probably don't want to click on. So how do we defend against this? Well, we have some very abstract concepts that were proposed in a paper that came out some time ago. One is to enforce something called visual integrity. So if we ensure visual separation between things, if we ensure that important dialogues and content are visually distinct from, say, content that the attacker has control over, then we can be sure that the user will see what they're about to click on and know that they want to click on it. So these are all real-world examples. For Windows users, if you've ever pretty much done anything, like tried to install a program or maybe open a malicious, or not malicious, open an untrusted website or something, I don't know, then this dialog will pop up and it'll make a noise and everything else will go dark. And this is because the user or Windows wants to make sure you know that this is a user account control dialog, so it's going to make everything else less visible so that you can focus on what you're doing. And there's no way that any program can fake this pop-up, because no program can make the screen darker, no program can take complete control of your mouse and not let you click on anything else. In another example, if you look at Firefox, and I think Chrome does this too, there are these dialog boxes. If you click on maybe this padlock here, you'll see that this is where the content of the website starts. This is our CS161 website. And this dialog box sort of passes over that boundary into the top bar here. So website content can't do that on its own. So we know that this dialog is created by the Firefox browser itself. It's not being faked by some content on the website itself. We had the space aspect. We can also enforce temporal integrity. So this has to do with time. We want to make sure that if something changes, let's say suddenly a dialog box pops up, we want to give the user enough time to register that, something has changed, and register the fact that maybe they don't want to click. So again, I'm referencing Firefox because this is the browser I'm using, and thus it's the one I'm familiar with. For download boxes, if you are also a fellow Firefox user, you may have noticed that when you try to download something, you can't actually click on this OK button. And this is for those temporal attack reasons. If you try to download something, then it's going to say you're trying to download, I guess in this case, Slack, and it'll give you a second to notice that now I'm downloading Slack before this OK button actually pops up. And if I navigate away from it and navigate back to it, then that OK button will be grayed out for another second. So no matter what you do, that dialog has to be on screen and unchanged for at least a second before it will let you download things. So if, say, some malicious website tries to make this download pop up right before or right as you're about to click on something, you're just going to end up clicking on the grayed out OK button, and then you'll have time to notice that something has changed. So those are our two main ways of defending against things and enforce. Oh shoot, I actually forgot what it's called off the top of my head. Enforce visual integrity and enforce temporal integrity. There are also more technical ways that we can do things. So if you're writing a website, maybe you want to require confirmation. So the browser will ask, are you sure you want to do XYZ? Are you sure you want to download this program? Are you sure you want to navigate to away from this website? This kind of annoys users. I have personally been annoyed by when websites ask me like 3 or 4 times, am I sure I actually want to do this thing? So there's definitely, again, the motif of consider human factors here, but generally for important things like downloads or say account deletions, you should require confirmation. Even more technical defense is frame busting. So for the clickjacking attacks that involved iframes, we could say you're not allowed to load me. You're not allowed to load me as a website in an iframe. So if anyone tries to do that, just block it and return an error. This will defeat the invisible iframe attacks, and we can enforce this either using content security policy, or there's an older HTTP header called xframe. It's not super important that you remember these exact names, but for certain clickjacking avenues, this is how we would probably want to defend against it. Questions on clickjacking? All right, I think we have enough time. We're going to take a 5-minute break. I'm going to go grab some water because my water pitcher is out, and we'll be back at 4:29. All right, so that is clickjacking. Now we get to talk a little bit about phishing. So I think many of us have received these emails in the past where it looks like it's from Google or Microsoft, or in this case, PayPal, and it says something urgent. Your account will be closed and you have to go do something. I don't know. Basically, just click on this link, please. Thank you. So we go to click on it, and if you notice down here, it's not paypal.com. It's this random website that we have never heard of before. But when we get to this website, it's fairly convincing. It looks like PayPal. I can enter my email and password. So why don't I just do that? Again, I didn't make these slides, but I don't know if Lady Gaga is still relevant. It takes us to the next page, and it still looks like PayPal. We've got the logo in the corner. I don't think they would ever say PayPal informations, but it's fine. So we say, okay, we'll just enter our info here as well. Go to the next page. It says, oh, we also need your credit card number to confirm your account. Please just enter it. Why not? You say, okay, well, that's a lot of information you're asking me, but maybe PayPal needs to check something and look at the thingy. I don't know. So we go and enter that in, and suddenly we're brought to the site. And at this point, we notice, why is it asking us to log in again? Well, it says we're on PayPal, so we're probably fine. I'll just go and log in again. When what has actually happened is, if you look at this top address bar here, this is not paypal.com. This is just a website that looks like paypal.com. And at the end, it's just redirected us back to the real website to try to cover its tracks. So that is phishing in a very small nutshell. We want to trick the user into sending the attacker personal information. The main vulnerability here is, again, with the user. They can't distinguish between a legitimate website, so the real PayPal website, and a website that's impersonating the legitimate website. So in this case, the website was impersonating the real PayPal.com website. And if you look at the HTML and you just copy it, it's actually fairly easy to do this. So this is a pretty prevalent attack. There are a couple things that I think a lot of people always hear. Maybe we can check the URL bar. Does this look like a real website? Who says it's real? And if you think it's fake, why do you think it's fake? Or if you want to say real just to keep the lecture moving, that's also fine by me. All right, we've got SSL connection and real question mark. I don't know if you actually think it's real or if you want to keep the lecture moving, but in fact, this one is fake. If we look down here, we'll see, look at this entire domain, and we see it ends in .var.cn. And what's actually happened here is someone has gone and registered a domain the full domain is www.pnc.com. There's a slash character, which is just part of the domain in this case, web app slash, again, part of the domain, unsec slash homepage, and then you need to have it as a subdomain of a real website, so it's still .var.cn. And Reza, I don't know if that's how you pronounce your name, but you pointed out the SSL certificate. And the issue here is that this is still a valid domain. I can still register a certificate for www.pnc.com/webapp/unsec/homepage.var.cn because I do technically control this domain. So if I went and looked at the certificate, I would see that the certificate is for www.pnc.com/webapp/unsec/homepage.var.cn. So that also brings up the point that we can't just rely on the SSL certificate, because the SSL certificate just says you're talking to someone who owns this domain, but it doesn't necessarily ensure the identity of the website. So in this case, no, this is not real. This is fake. All right, how about this one? Should be fairly easy. Real or fake? I know none of you want to say real because I know you think this is a trap. Real. You're right. It's fake. This is a really subtle attack, and it's defended against in some browsers, but not all. This one is Firefox, and unfortunately, Firefox is still vulnerable to this. These letters, this may look like APPLE, but these are actually from the Cyrillic alphabet. So the Cyrillic alphabet is just a different alphabet used by some languages. And its letters look the same as the Latin alphabet, which is what's used, say, on your keyboards, but they have completely different bytes. So this isn't, APPLE as you would type on a keyboard. It's 5 letters that look like APPLE, but in fact, they're completely different characters. So this one was really subtle. I think it's really clever. I love it. But both of these are examples of something called homograph attacks. So the overall idea is, if we just check that the URL is correct, does that give us the guarantee that we're looking at the right website? And the answer to that is no. We can create malicious URLs that look similar, or in the case of this one, identical to legitimate URLs. A homograph just means 2 words that look the same, but they have different meanings. So this is why it's called a homograph attack, because they look the same, but they're 2 completely different websites. Okay, maybe let's not just check the URL. Let's just check everything on the website. And so here we have this green thing here. So this actually says, this SSL certificate doesn't just say, this is www.bankofthewest.com. It actually says we have verified that this belongs to the corporation called Bank of the West, and we've signed that as part of the certificate. So this certificate not only attests to the website, but also the identity of the server, right? Maybe, maybe not. This is also something that happens. Sometimes you will go to a website, and this website renders an entire browser with JavaScript that looks like it's go at the correct site. So in this case, what we've done is, because now we're inside, our own web page, this JavaScript has control over this entire emulated browser. So oops, this is actually not real. It's just someone has emulated an entire browser inside our browser. So this is a browser-in-browser attack. And yeah, it's kind of weird, but it works on enough people that it's in pretty widespread use from time to time. We can't rely on built-in browser security features if the JavaScript can just render an entire browser inside and then just fake those security features. So yeah, just simulate the entire browser with JavaScript, and then you can simulate these features without actually having to compromise the certificate or anything. So these are all really subtle attacks. And I think whenever we talk about phishing, there's always someone who says, it's just the user's fault. I mean, we should have trained the users. The users shouldn't, they shouldn't have clicked on this link. But it's a little more subtle than that. Most users aren't security experts, and I don't think we can expect every single human on Earth to go through like a completely intensive training course on how to not be phished, because that would be too difficult. And we do require that sometimes, but the issue is that attacks are so uncommon that it's impossible for anyone to always be checking every single part, always be checking that your browser isn't run inside another browser, always check, for the green padlock or the URL, or check the letters in the URL. They just aren't common enough for users to check all the time. So users let their guard down and they don't suspect malicious actions. And even if you are trained, it can still be really hard to detect whether you are being phished or not. I think this one especially is a great example of that, because this looks like apple.com. I would totally believe this for apple.com if someone put a phishing site on here. Fortunately, someone hasn't. And I think if you actually look up Cyrillic alphabet homograph attack, you can find this website. But basically, it's hard to detect phishing attacks. So we can't just blame the users. It's also on the tools that we use. And sometimes we even train users to be phished. So if you've worked at some company that is concerned about phishing attacks, sometimes you'll receive these emails that say you've been assigned to take the UC Cybersecurity Awareness Fundamentals. Please click on this link and go learn how to not be phished. So it's ironic because we tell users the best way to say not be phished is to, for example, just look up the website on Google and then go to it. And yet sometimes we fail to actually train users to not be phished because we give users links to where they want to go. So all of this is sort of a weird trade-off between considered human factors and also the tools that we use aren't great. Basically, don't blame the users. There are defenses in place. The main one here is two-factor authentication. For phishing, usually attackers are after passwords because they allow the attacker to log in as the user. So if we have some sort of security measure in place to require more than just passwords, then we can start to defend against these attacks. So when we talk about two-factor authentication, or 2FA, we say that the user has to prove their identity in not just one way, but two different ways before they actually authenticate. There are three main classes of ways that we talk about when we talk about 2FA. So the first one is something the user knows. Maybe it's a password, a security question, which is oftentimes like the name of your first pet or the name of your high school best friend or something like that. The next class is something that the user owns. So this could be your phone, maybe this is access to your email, or maybe this is a security token that you literally keep in your pocket. And the final thing is something that the user is, something you are. And these have to do with biometrics. So if you have a fingerprint sensor, or if you have an iPhone and it has Face ID or Windows Hello, which sort of does the same thing, these are associated with like literally who you are. in movies, you'll see like retina scanners or I don't know, DNA, something or other. Those would also fall under the category of something that the user is. The idea here is that even if the attacker steals a password, they won't have access to that second factor. So this defends against other attacks as well if the user's password is compromised. Oops, I lost control of the, there it is. For example, if the attacker doesn't phish the user, but the attacker steals a password file and is able to perform a dictionary attack to crack some of the passwords, then the user, say they reused that password from other websites, then the attacker has the ability to log into other websites using that same stolen password. If we have 2FA, then this isn't possible anymore because maybe the attacker has the first factor, the password, but the attacker doesn't have the second factor needed to log into that other website. So this defends against any time your password is leaked. Of course, with any defense, there are ways to subvert it. So the most easy to reason about is a relay attack. So with a relay attack, also called transient phishing, this is just the attacker stealing both of these factors at the same time. So as an example, maybe our scheme is that the first factor is the password, and the second factor is a code that your phone generates, and then you have to type that code in to send to the server, which would be something the user owns. Our attack, in this case, would be the phishing attack from before. So the phishing attack still just steals their password. And then let's say that the attacker tries to log in, and the attacker is presented with this dialog to enter their code. So now the phishing website, or the actual website, will send that code to the user because it's something that they own. The user is still being phished at this point, so they enter their code into the phishing website, then the attacker receives this and enters it into the real website. So now the attacker has just phished both factors out of the user instead of just the password. I see a backtick in chat. I think that might have been an accident. All right. So just to diagram this out, the attacker gives a fake website to the victim. The victim enters their password. The attacker goes and enters the password into Google. Google sends a code to the victim. Now the attacker presents the phishing website presents the security code prompt. The victim is still vulnerable at this point. They enter their code, and then the attacker can finish the login with Google and enter their 2FA code. So, and this is, for certain 2FA schemes, it's vulnerable to these transient phishing attacks where the attacker basically just phishes everything, not just the password. There are also social engineering attacks. So we're still talking about considered human factors here. For some 2FA schemes, this relies on texting a code to a phone number. So I log in, and then some machine sends like a literal phone text message to my phone. The attack is tricky here, but the attacker can call your phone provider, say you use Verizon. They call Verizon and say, hey, I lost control, or I lost my SIM card. Could you activate my new SIM card? And like, here's the ID of it. And they say, oh, I'm sorry to hear that. I'll go ahead and do that for you. So suddenly the attacker has a SIM card that's associated with your phone number. And now the attacker is the one receiving your text messages. The result here is that 2FA for using SMS is not great. It's better than nothing, but we've seen these social engineering attacks before where customer service will bypass the 2FA scheme for you, which ends up subverting it in exchange for convenience for the user. So if the attacker calls customer support, asks them to deactivate 2FA, and they don't validate your identity, and they just do it, then the attacker has now just bypassed 2FA in this case as well. So there are always social aspects to computer security, and 2FA is one where it's particularly prevalent. Another example of 2FA would be something called an authentication token. So if for most schemes, I think this is what most schemes use, If you have some QR code that you need to scan onto your phone or something, and then that phone generates like 6-digit codes, this is that authentication token scheme. So in this case, it's something that the user owns because that code sits on your device and you can't possibly memorize like a 256-bit symmetric key. So it has to sit on your phone. So if you have RSA Secure ID or Google Authenticator, this is an example of that. This relies on cryptography. So in this case, the token and the server will share a key K. When the user wants to log in, the token has an algorithm where it just basically computes an HMAC with the current time. So that HMAC becomes the code. Often this time isn't like down to the second, so you can be anywhere within a 30-second window. And we cut it down to 6 digits because you don't want to enter a 256-bit HMAC into your browser. Once you have this code generated on your phone, you send it to the website, and the website has the same algorithm. So the website will use the same key to generate the HMAC for the current time and check, does it match the code that was sent to me? So you can sort of reason about on your own the guarantees and why you would want to use HMAC. But this ensures that the user meant to generate their code because only, in theory, only the user has access to that key to generate the HMAC. Unfortunately, this is vulnerable to that relay attack earlier because if the attacker receives this one-time code that's generated every 30 seconds, then the attacker can just forward it on to the website. It's also vulnerable to online brute force attacks. So for some websites that don't have safeguards set up, because it's often truncated to 6 digits, there are only a million possibilities for the attacker to try. And for certain cases, this might be small enough to brute force and just get past that 6-digit code. So it's not a perfect system, but it's better than SMS because there's no way for the attacker to social engineer, at least for SMS. The attacker can still social engineer for customer support though. I also did not set up transitions for this slide, so you're going to get a wall of text. Nope, never mind. This is the same text. There is a fix to the online brute force attacks. It's the same as before. You just add a timeout, and this means that the attacker can only try, say, once every 10th of a second, and then this causes a million inputs to take, what would that be, 10,000 seconds, which is long enough that it probably doesn't matter. All right. The second example of 2FA that we'll look at is security keys. So a security key is a second factor designed to defend against phishing. So this has cryptography in place that will prevent even the relay attacks or transient phishing attacks. Again, this is something the user owns because, for example, this is a security key that I own. You cannot log into a lot of my accounts without the security key. The usage here is that when the user signs up, the security key will generate a public-private key pair, give the public key to the website, and the private key is just stored on the key itself. It's stored on this tiny chip that you can't really access. When you want to log in, the server is going to send some random nonce to the browser. The browser sends that nonce to the security key, and then the security key will sign it inside the key itself. So security key never releases the private key itself. It just takes in the nonce, signs it, and then gives the signed output. This signature is also going to include the website name as well as the ID of the key, just to defend against other attacks that we'll get to in a moment. And this is actually 100% effective against phishing because in a phishing attack, the security key generates a signature with the website name. So if we're on some attacker's website with a different domain name, then this signature is going to say, here's the nonce signed for attacker.com. And then when bank.com receives this, it sees, here's the nonce that I sent it, but it was signed for attacker.com, not bank.com. So I know that this is not a valid signature. I'm not going to let the users through. So it completely blocks the relay attacks unless the attacker has some way of taking over the domain itself, which we assume that they can't do. All right. I know that was a lot. That was a lot about both human factors and a lot about technical jargon about how data is processed. But just to summarize, for XSS, the overall vulnerability is that websites will sometimes use untrusted content as control data. So for something like Hello Evan bot, the browser receives this and just displays it normally. But if the browser receives hello script alert 1 script, the browser is just going to see this, treat this as, oh, this is code that I should run that, and maybe this code is malicious and causes the browser to send secret data to the attacker or do malicious actions for the server with the origin of the client or of the website. The two classes are stored XSS and reflected XSS. So stored XSS is when the payload is stored on the server itself. So maybe it's a Facebook post, or maybe it's a comment on a YouTube video. And for reflected XSS, this is actually input that's in the request itself, and it's just reflected back to the user. So the classic example is the search engine, where it says you searched for, say, emus. I don't know. But if it says you searched for script alert 1 script, then that's going to run in the browser again. For defenses, generally we use HTML sanitization. So we make sure that any control characters get turned into sequences that will only ever be interpreted as data. So we have the less than becomes the &LT, and the quote becomes &QUOT, and make sure you always use libraries to sanitize for you. There's also the content security policy, which can prevent resources from being loaded from places that you don't trust and prevent inline scripts from being run in the browser. This has to be browser enforced, so some browsers don't support it, and that's why it's better as a defense and depth measure than full protection against XSS. For UI attacks, we talked about clickjacking, where we want the victim to click on something that the attacker wants them to click on rather than that the user wants to click on. So the browser trusts what the user clicks on. So if the user clicks on, for example, fake download buttons or a invisible iframe or something that pops up right before they meant to click on it, or maybe they click on something when they thought the mouse was somewhere else, these are all trusted inputs to the browser, and the browser will just assume that that's what the user actually meant to do, and they'll just do that malicious action. For defenses, if we enforce visual integrity by focusing the important parts and defocusing everything else, that lowers the chance that they'll click on the malicious thing. If we enforce temporal integrity, that gives users time to register if something has changed, gives them time to read it, and then not click on malicious things. We can talk about confirmation, so just ask them several times and make sure that they want to do it. And then on the technical side, we can do frame busting, where the legitimate website just basically tells web browsers to never embed it in other iframes. Finally, for phishing, where the attacker tries to get the user to input their personal information, they usually create a malicious website that looks like the real website and tricks the user into entering their password or credit card info. You shouldn't blame the users for phishing because it's hard to detect, and there are always ways to fool a user, even going as far as to put a fake browser in the real browser and cause the user to think that that is the real browser. To defend against this, generally, it's just two-factor authentication, where you prove your identity using multiple of something you know, something you own, and something you are. This defends against attacks where the attacker has only stolen, say, the password or one of the other factors, but is vulnerable to relay attacks where the attacker can just trick the victim into giving them both the factors, and it's vulnerable to social engineering because oftentimes customer support will just bypass 2FA for you. We talked about authentication tokens as an example of 2FA, and we talked about security keys, which are much better than authentication tokens, and they're impervious to phishing attacks altogether. But yeah, that brings us to the end of this lecture with 5 minutes to spare. Ironically, I just received a text with a link in it. Should I click on it? I don't know. We'll see. But yeah, that brings us to the end of today. Are there any final questions before we head out? All right. In that case, I will see you all tomorrow.